So it's now just after 7 a.m. and as you can see, the sun is up and the telescope has been doing its thing all night, just pointing directly at the south celestial pole, taking one frame every 7 seconds. So in this video we're going to look at some star trails that were taken from Perth a couple of weeks ago when I had my telescope pointed towards the south celestial pole. As you can see, it turned out very nicely. But as you watch the time lapse progress, I want you to notice a number of things. Number one, every star is moving at the same angular rate around the central point. Additionally, there is absolutely no overlapping of any of the stars. They are very precisely spaced, and that spacing doesn't change whether they are at the lower part of the image or at the top. Now, I have seen in the past some flat earthers claiming that the star trails will overlap, but that's what happens if you put your tripod on soft earth or grass and it settles by a few millimeters overnight. When the telescope is placed on a steady tripod on a solid base, the star trails are extremely precise, as you will see here. So the time-lapse consists of more than 3,000 individual photographs, with one taken every 7 seconds. If we choose a random sample, it looks like this before being processed into the time-lapse. We're now going to do a plate solve on this image to confirm we are looking at the south celestial pole. And we do that with this website, nova.astrometry.net. We select Upload. We choose our file. And we upload it to the site. Now at this point, the analysis only takes a minute or two, so I'll let it run in real time. And what the software is doing is analysing the stars it can see in my photograph and comparing it to a known database. Once the analysis is complete, it will tell us information about the photograph and also exactly what part of the sky we are looking at. We now go to the results page. And if we overlay the grid, you can see that we are in fact looking at the south celestial pole. We have additional information over here. The size of the image is 105 by 58.9 arc minutes, so roughly 1 degree by 1.7 degrees field of view. We also have images down here that show us where our photograph is in relation to other objects in the sky. So at the end of this video, I'm going to play another time lapse taken without the star trails, and this one has a timestamp in the upper right hand corner, and it goes right through until dawn. What I'd like you to be mindful of as you watch this time lapse is that any of the stars in view can be tracked with an equatorial mount using a single axis of rotation at a steady, unchanging rate. Now it's worth reiterating this point because the geometry of the equatorial mount is an absolute flat earth killer, and any flat earther denying this is really just telling us that they still don't understand how an equatorial mount works. So please feel free to go ahead, fellas. If you want to show the world that you still don't understand how the EQ mount works, be my guest. So here it is, the equatorial mount, one of my favourite flat earth killers that provides measurable proof that the earth cannot be flat. I wonder how many flat earthers are going to show us once again that they still don't understand how this mount works. If we were tracking any of those stars near the South Celestial Pole, the geometry might look something like this, and the tracking will occur on a single axis of rotation, like this. Now the part that destroys flat Earth is the fact that we can track on a single axis of rotation at a steady rate when that axis is polar aligned, and that means aligned according to latitude. What is quite fascinating though is that we can point it to any star in the sky and it will still track that star using that single axis of rotation at the same rate. No matter where you are on the Earth, that single axis and steady rate of rotation will track any star in the sky. I have no idea why flat earthers still don't understand this, but I guess it just boils down to their inability to comprehend basic math and geometry.